As we move into section 5.5, we've gone past our sum and difference identities into our double angle identities. So if you've got your identity sheet handy, you can see that you have this big section here of product to sum and sum to product. And right down here, we've got double angle and half angle identities. So these are the two sections, all of these formulas, all of these identities that we're going to be talking about in this section and in 5.6 as we wrap up chapter 5. Okay, now double angle identities. We derived one of our cosine sum, I believe, or no, sine sum. We derived the sine sum identity, and then we didn't derive the others. We're going to go ahead and we are going to derive our double angle cosine identity. We're going to figure out how we get that double angle cosine identity. Now, one thing that I want to point out is that cosine of 2a, I'm doubling my angle, is not the same thing as 2 times the cosine of a. That is just like when we did cosine of a plus b is not equal to cosine a plus cosine b, and we showed why that did not happen. Just like that is the case, cosine of 2a is not the same thing as 2 times the cosine a. If that were the case, then I could say that if that were true, 2 times the cosine of 30 degrees would be equal to the cosine of 60 degrees, because 2 times 30 is 60, right? So I need to see if that would be true. In this case, a would be 30 degrees. 2 times the cosine of 30, is that equal to the cosine of 60? Well, if you look at your identity sheet, the cosine at 30 degrees is square root 3 over 2, and cosine 60 degrees is 1/2. If I multiply this and simplify here, I've got square root 3 equal to 1/2, which is not true. So you see that that mathematically does not work. And if it doesn't work one time, that disproves my idea that that might be how to do that identity. Now, cosine of 2a is, however, equal to cosine of a plus a, because a plus a is the same thing as 2 times a. So these two arguments are equal to each other. And this is my cosine sum identity. So I can say, okay, well that would be cosine a minus sine a sine a. And cosine a times cosine a is the same thing as cosine square a. Sine a times sine a is the same thing as sine square a. And that is the first of my options for my cosine double angle identity. Cosine square a minus sine square a. That's the first one. But wait, there's more. Because I can use my basic foundation Pythagorean identity. Go back to those fundamental identities. My primary Pythagorean identity, sine square theta plus cosine square theta is 1. So I can replace that cosine square theta with 1 minus sine square theta. So I can take that out and I can say, okay, that's the same thing as 1 minus sine square a. And then I've still got this minus sine square a. So that gives me 1 minus 2 sine square a. That's my second option for a double angle cosine identity. Cosine of 2a is equal to 1 minus 2 times sine squared a. Or I could go from here sideways and replace the sine square. Well, if I replace that, I would have cosine square a minus, and then my substitution in here for sine square would be 1 minus cosine square A. So that yields cosine square A minus 1 plus cosine square A, which gives me 2 of those cosine square A minus 1, and that's my third option for my cosine double angle identity. I have 3 different options for cosine double angle. Now there's only one option for sine double angle, only one option for tangent double angle, and we are not going to take the time to derive those two. I'm just going to give them to you. Sine double angle is 2 sine A cosine A, and tangent double angle is going to be a quotient, just like my tangent sum and difference identities, 2 tangent A over 1 minus tangent squared A. Okay. So let's go on into an example where we're finding function values of a double angle given information about an angle. Well, I'm told that sine theta is 8 over 17 and that cosine theta is less than 0. So cosine is negative. I'm asked to find sine of the double angle, cosine of the double angle, and tangent of the double angle. So the first thing we're going to do is we're going to take our value for sine of theta and we are going to find cosine of theta. Now this is going to get me to where I need to be so that I can find the values for 2 theta. First I have to know some things about theta. Well, we could draw our sketch and find our missing value, but we're going to choose to use our Pythagorean identity, cosine squared theta plus sine squared theta equals 1. I know sine, so I've got cosine squared theta plus 8 over 17 squared equals 1. Well, I'm going to subtract that from this 1, so I need to know what my denominator is going to be. 17 squared is 289. So when I rewrite this to finish solving for cosine, I subtract this over. I'm going to rewrite my 1 as 289 over 289, so that when I subtract this, 8 squared is 64, 17 squared is 289, I'm going to be able to have that common denominator and do that subtraction. So cosine squared theta is equal to 225 over 289, and then to finish solving, I need to take the square root of both sides because that's how I unsquare this cosine square. Typically when I take the square root to solve, I consider plus or minus, but we have been told that cosine is going to be negative. It's going to be less than 1. So I automatically know the sign, the algebraic sign of this function value. I don't have to leave it there. Now square root of 225 is 15. And I know the square root of 289 is 17 because that's how I got 289. So cosine theta is a negative 15/17. And now I can use my identities to find the values I'm asked for. So this was my starting place. This is not an answer that I was asked for, but now I can find these answers. Okay, next I'm going to move into solving my problem. I'm going to solve sine of 2 theta, the double angle, and I only have one option for a double angle sine identity. So I'm going to have to use 2 sine theta cosine theta. That's my only option. But I know sine theta and cosine theta because we were given one, we found the other. So I've got 2 times sine theta was 8 over 17. Cosine theta we found to be a negative 15 over 17. So positive, positive, negative is going to give me a negative value. 2 times 8 is 16 times 15. I'm going to have to plug that into my calculator because I can't do it in my head. I get a negative 240. I already know from the previous work that 17 times 17 is 289. And that's the sine of my double angle. That's the first problem I was asked to figure out. The next problem I was asked to figure out, so this is sine of the double angle. Let's do cosine of the double angle. Now, when I go to my cosine, I've got choices. I have 3 choices to be exact. for my double angle cosine identity. Deciding which one I use, I could really use any of them, but remember the idea that we always want to use the givens if you can. Well, for this one, I only had one identity for sine double angle. I had to use this found value for cosine. But when I do my cosine double angle, I can stick with just this second option and I use my given. So if my value for cosine theta happened to be wrong, I'm not starting out with the wrong amount. So I'm going to choose to use 1 minus 2 sine squared theta as my double angle cosine identity that I make use of. So that's 1 minus 2 times, and then I've got sine squared. Sine was given to me as 8/17. Order of operations is important. I know that when I square this 17, I'm going to get 289. So that 1 gets rewritten as 289 over 289 minus, before I multiply in the 2, I have to square the 8. Order of operations. 8 squared is 64 times 2 is 128. Yep, 128. If I did 2 times 8 is 16 and then squared it, I would get the wrong answer. So make sure that you follow your order of operations, parentheses and exponents first, and then I multiply and divide. Okay, 289 minus 128 is 161 over 289. So there is my cosine of the double angle. And now we've got tangent of the double angle. That's our last thing we were asked to find, tangent of the double angle. We only have one double angle tangent identity. So we will say, okay, we've got tangent of 2 theta is going to be 2 tangent theta over 1 minus tangent squared theta. Well, what is tangent theta? Tangent is sine over cosine. Cannot get away from using my found value here. So tangent of theta is sine, which I was given, over cosine, which I found, negative 15 over 17. Those 17ths are going to cancel out when I multiply by the reciprocal, and I have a negative 8/15 for my value of tangent of angle theta. So here we go. 2 times tangent theta over 1 minus tangent square. So my numerator, 2 times tangent theta gives me negative 16/15. My denominator, 15 squared, is going to be 225. So my denominator, that 1 needs to be 225 over 225 minus negative 8 is a positive 64 over 225. So I've got negative 16 over 15 as my numerator. My denominator comes out to be, oh, I can't do that. Yeah, 161. 161 over 225. I've got this big rational expression, this big ugly division problem. I solve it by multiplying by the reciprocal. 15 is going to cancel, so that I've got 15 times 16. It's going to give me a negative 240 over that 161. Alright, so we were using values of theta to find our information about the double angle 2 theta. Okay, let's look at our next example, see what we do from there. Now we're told to find the values of the 6 trig functions of theta when we're given information about the double angle. Now, what do we know? We know that our angle theta, the angle we're interested in, is in quadrant 2. How do I know it's in quadrant 2? Well, if it's between 90 and 180 degrees, we're in quadrant 2. And in quadrant 2, our cosine function is negative and our sine function is positive. Now, we are given cosine of the double angle. And we need to find all 6 trig functions from that. Now, when I look at my cosine double angle identities, I've got 3 options. I don't want to use one with both sine and cosine because I can't solve for both of those at the same time. I'm going to have to pick one of these 2. And it doesn't matter which one we pick. I'm going to go ahead and go here just because that's the one I've already got down in my notes, but I could just as easily have gone with this one and solve for sine instead of solving, or solve for cosine instead of solving for sine. But we're going to use this one because that's the one I have down. So my double angle 2 theta is equal to 1 minus 2 sine squared theta. That's the identity I'm going to use. Now I was given this double angle value. Cosine of 2 theta is equal to, cosine 2 theta is equal to 1 minus 2 sine squared theta. I know that cosine of 2 theta is 4/5 because that's what I was given. So 1 minus 2 sine squared theta, I'm going to subtract this 1. Well, when I subtract the 1, it comes over as a negative 5/5, right? Because I need to subtract it from 4/5. So 4/5 minus that 1 gives me a negative 1/5 equal to a negative 2 sine squared theta. We subtracted 1, got our negative 1/5 over here. Now I'm going to divide by that negative 2. Division with fractions is multiplying by the reciprocal, so I can multiply by 1/2. Negative times a negative is going to be a positive. I get a 1/10 is equal to sine square theta. Take the square root of both sides to solve, and I know that I'm in quadrant 2, so that sine is going to be positive, which gives me, square root of 1 is just 1, so 1 over square root 10 is sine theta. Need to rationalize, and I get square root 10 over 10. So that's my value of sine. But what does this tell me? This bit tells me that y is 1 and r is square root 10. I need to know x. Well, if y is 1 and r is square root 10, I'm going to use my Pythagorean theorem. X squared plus y squared equals r squared to solve for x. So x is equal to the square root of r squared, square root 10 squared is going to be 10, minus y squared, 1 squared, is 1. 10 minus 1 is 9, 10 minus 1 is 9, square root 9 is 3. And because I'm in quadrant 2, I know that x is going to be negative. So there are my 3 values, x, y, r. I'm going to use those to give me my 6 trig function values that I'm looking for theta. So I was given cosine of the double angle. I started by finding sine of theta. I rationalized it to be square root 10 over 10. Reciprocal of sine is cosecant. That's just going to be square root 10 because that's what I started with when I take the reciprocal of that. Alright, cosine theta, x over r is going to end up, when I rationalize it, as negative 3 square root 10 over 10. But it started as negative 3 over square root 10, right? So when I flip that, take the reciprocal to get my secant function value, I have a negative square root 10 over 3 for secant. Tangent theta is y over x, so that is a negative 1/3, which means cotangent theta is a negative 3. And there's my 6 trig function values. Alright, let's do some verifying. If we verify double angle identities, we're going to make use of our algebra solving, factoring skills that we know. Over here, I've got cosine, let me autofocus to see if we can make this any clearer. I've got cosine to the 4th beta minus sine to the 4th beta equals cosine of 2 beta. So I want to end up with this double angle, but we're going to start because I've got like 3 different directions to head here and I don't know which way to go. So we're going to start over here. This is a difference of squares. Difference of squares factors out to give me conjugate pairs. So that would give me cosine squared beta plus sine squared beta times its conjugate, cosine square minus sine square. And this is my fundamental Pythagorean identity. That is my Pythagorean identity. It's just 1. So I've got 1 times this cosine square beta minus sine square beta. And if I look at my list of identities, because I know where I want to head, that's one of my double angle identities. That is cosine of 2 beta. That was my goal. But I do need to show this step here so it doesn't look like I just guessed. Okay, let's verify this one. Show how it is an identity. We've got cotangent x times sine of the double angle. We want to end up with 1 over cosine double angle, 1 plus cosine double angle. Okay, so where do we want to start? Well, I'm going to start on that left side. I'm going to go ahead and change cotangent to sine and cosine, and I only have one option for sine double angle. So cotangent is going to be cosine x over sine x. Make sure you use the argument that you were given in the problem. My double angle sine identity is 2 sine x cosine x. That's the only one, the only option I have. Because I'm multiplying this times a fraction, I go ahead and put it over 1, just because it makes me happy to keep things balanced. That sine x is going to cancel out, so that I have 2 cosine square x, 2 times cosine square x. And how does that help me? Well, I need to end up with this, and I see that I've got this double angle over here. I've got a 1, and I've got this cosine square. Well, right here, I can make use of this double angle identity. Remember, just like with our Pythagorean identity, we can rearrange terms. Well, if I solve this for 2 cosine square a, I would be adding that 1 over to the other side. So 2 cosine square x is the same thing as 1 plus cosine of 2x. And that's what I was after, because that is that rearranged form of my double angle identity. Okay. Please take advantage of that pause button. Anytime you need to pause, go back over, reconsider, re-listen to an explanation. We're going to spend a little bit of time practicing simplifying expressions using double angle identities. There's 4 examples here because these go really quickly. For example, number A, how about letter A? 2 cosine square 5x minus 1. Well, I know that one of my double angle identities, cosine of 2x, or it's listed as 2a, so let's just leave it as 2a. Cosine 2a, cosine double angle, looks like 2 cosine square a minus 1. Well, if I count 5x as a, right there, that becomes 5x. That means that this is equal to cosine of 2 times that argument, where my argument is 5x. So cosine of 2 times 5x gives me cosine of 10x. We did a substitution right there. We said, you know what? My argument a here is the same thing as 5x here. Alright, so what about this one? What does this one look like? Well, sine of an angle, cosine of an angle, and I'm charged with using double angle identities. What does that most resemble? Well, my sine double angle is 2 sine a cosine a, so let's start there. Sine of the double angle equals 2 times sine a cosine a. but I don't have that 2 there. So algebraically, I can divide both sides by 2. So that gives me 1/2 sine of 2a is equal to sine a cosine a. That's another way to write that double angle sine identity. Notice that when I divided this left side by 2, I multiplied that 1/2. I divided the whole thing by 1/2. I didn't divide the argument. I divided the value of sine. So this works where I consider a is 165 degrees. So I've been given this right side. I'm going to plug that 165 in over here. So 1/2 sine of 2 times 165 degrees. Well, that's 1/2 sine 2 times 165 is 330 degrees, and 330 is on my unit circle. It's one of my special angles. The sine function value of 330 degrees is negative 1/2, so this simplifies to be a negative 1/4. Notice that this one just simplified to be cosine of 10x, nowhere else to go here. This one gave me an angle measure that brought me to a special angle, and I was able to plug in that value. Alright, let's look at the next one. Cosine square 7x minus sine square 7x. Go look at your double angle identity sheet. This is cosine 2a equals cosine square a minus sine square a, where a is 7x. So I've been given this right side. I'm going to plug that, replace a as 7x into the left so that I have cosine of 2 times 7x. Well, that's just cosine of 14x, and there's nowhere else to go from that. And finally, sine 15 degrees, cosine 15 degrees. This one looks just like the one up above, where I'm using a as 15 degrees, and I have to adjust that double angle identity, divide both sides by 2. So I've got 1/2 sine of 2 times 15 degrees. Well, that's 1/2 sine of 30 degrees. And sine of 30 degrees is a positive 1/2. So there we go. All right, excellent. Okay, these next couple are a little bit longer. We may actually break this video up to do the product to sum identity separately. Let's see. Let's derive a multiple angle identity. There are an infinite number of identities. We are only given a select few common ones to work with. We want to write cosine of 3x in terms of just cosine x. So we want to end up with no other trig functions, no other arguments, no other trig functions than cosine, no other arguments than x. That's our goal, to rewrite cosine of 3x in terms of cosine x. Well, what is something that will help me to change this cosine 3x into terms I can work with? Well, 3x I could rewrite as 2x plus x. So let's do that. Let's do cosine of 2x plus x. 2x plus 1x is 3x, and this is a cosine sum identity. So let's use that. Let's do that cosine sum identity. Cosine of the first, cosine of the second, minus sine of the first, sine of the second. Well, I've got two things going on here that I need to deal with. I've got things other than cosine, and I've got arguments other than x. I've got these double angle arguments. Let's take care of the double angle arguments first. Let's take care of cosine 2x and sine 2x. Now, when I do cosine 2x, I've got choices. I've got 3 choices to be exact, but my charge is to end up with just cosine. So that is the double angle identity I'm going to pick here for cosine 2x. I'm going to pick the one that is just cosine. So that's going to be 2 cosine square x, 2 cosine square x minus 1 times cosine x That's that substitution right there. Minus, and then I only have one option for double angle sine, so let's just do it. Let's do minus 2 sine x cosine x, and then that's times sine x. All right, let's multiply things in where we need to. So right here, we're going to distribute this cosine in. So I have 2 cosine cube x minus cosine x. And when I multiply all of this together, I have a negative 2 sine square x cosine x. Well, we have almost everything we need. Our arguments are just x. We don't have any double angle arguments. But I do still have a sine function here. In fact, it's sine square. So I need to get this sine square out of there and get it just in terms of cosine. I'm going to use my Pythagorean identity here. My Pythagorean identity, sine square x plus cosine square x equals 1. So sine square x is 1 minus cosine square x. That's going to be my substitution right here. So let's do that. 2 cosine cube x minus cosine x minus 2 times my substitution times cosine x. Right there. There's my substitution for sine square x. Alright, so my first two terms are fine. I need to multiply and distribute all of this together, so let's do that. That's going to take me a couple of steps. Cosine cubed x minus cosine x. Let's distribute this negative 2. So we've got minus 2 plus 2 cosine square x. And then that is all being multiplied by this cosine x. So all of that, let's see, let's do plus a negative and then cosine x there. The best way to show how to do that. And then I'm going to distribute this one in. So I got minus 2 cosine cube x minus cosine x minus 2 cosine x plus 2 cosine cube x. So we've got 1, 2, 3, 4 terms. We want to combine like terms. We've got 2 cosine cube terms, so there's 4 cosine cube x. And then we've got those two that are just cosine x, so minus 3 cosine x, and we're done. Cosine of 3x is the same thing as 4 cosine cube x minus 3 cosine x. Ta-da! Alright, so that is how we get a multiple angle identity bigger than cosine 2x, more than a double angle identity. We've got 2 more pages. I think that we can make a go of this. If you need a break while you're watching, you get to take your break. You know what we're going to do? I'm going to skip to the end of this one. This is a good one for you to practice without me leading you through, holding your hand. We're starting with sine of 3x. We want to end up with just terms of sine x. And I'm going to tell you, you're going to start by looking at it the same way we did with cosine. We're going to look at it as sine sum, where you have 2x plus x. And then you need to get it in terms of just sine, argument just x. When you get done, down here at the end, you should end up with 3 sine x minus 4 sine cubed x. I'm not going to show you the steps from here to there. I'm going to let you practice, not try. I'm going to let you practice and see how to get from here to there on your own. And we are going to move to product to sum and sum to product identities. We've only got a few examples here. Mostly it's copying down those identities and talking about how to derive a couple of them. Sorry, my throat gets dry. Okay. So let's derive one of them. We're going to do it by adding identities together. If I add cosine sum to cosine difference. Cosine sum to cosine difference. We're going to add those two together. Well, cosine sum is cosine A cosine B minus sine A sine B. Cosine difference is cosine A cosine B plus sine A sine B. Over here on the left, these are not like terms. They are not the same argument. So I just have cosine of A plus B plus cosine of A minus B. Over here on the right, these two are like terms, so I have two of those. But these are opposites, so they add to 0. They add to 0. Well, I'm deriving this product to sum identity, cosine A times cosine B. So I want to get its cosine A times cosine B. The only thing I have to do to make that happen is to divide everything by 2. Which means that cosine A times cosine B is equal to, now dividing everything by 2 is the same thing as multiplying by 1/2. So it's 1/2 of cosine sum plus cosine difference. Alright? Ta-da! That's how those identities, product to sum, tie together to what we've been doing so far. Now, notice product to sum, we're starting with products, we're ending up with sums, and a sum and a difference is just adding a negative, right? So, let's go ahead and copy these down. Notice that for sine A, sine B, you have your cosine difference minus the cosine sum inside my brackets. You don't have to memorize these, but you do have to pay attention to where those algebraic signs go, those pluses and minuses. That makes a big difference. And then here we have 1/2 of sine sum plus sine difference. And here we have 1/2 of sine sum minus sine difference. Those are all on your list, that big long list of product to sum, sum to product identities right here. Alright, how do we use those? Well, using them is pretty easy. You just have to recognize which one you're interested in. I've got sine of 46 times sine of 40 degrees, sine of 15 degrees. Well, sine and sine, this is A, this is B. Sine A, sine B, that's the second one right here, right? I'm looking at, I'm saying, okay, well, I've got sine A, sine B equal to 1/2 of cosine of A minus B minus cosine of A plus B. And what I've done here is I've multiplied this by 6. So if I'm going to multiply one side of my identity by 6, I've got to multiply both sides of the identity by 6. A is my 40-degree angle, B is my 15-degree angle, because this is first, this is second. So let's use that. We're going to say, okay, I've got 6 sine of 40 degrees, sine of 15 degrees. So that's going to be equal to 6 times 1/2 times cosine. Well, A is 40 minus 15, all degrees, don't forget your degree symbols, minus cosine of 40 plus 15. I'm just plugging in what I'm given. I find the one it's like. I make any adjustments I need to make. Here I had to multiply in the 6. So what is this the same thing as? Well, it's the same thing as 6 times 1/2 is 3 times cosine of 40 minus 15 is 25 degrees minus cosine of 40 plus 15 is 55 degrees. Neither one of these is a special angle, so I'm done. I wrote it as the sum or difference of two functions. Let's do another example like that. I encourage you again to pause. Take advantage of that pause button. See if you can do this one on your own before you look to see what we did. I've got cosine, sine. And when I compare my identity sheets, I've got cosine, sine, cosine, sine. It looks like this last one right here. So I've got 4 times cosine 75 degrees, sine 25 degrees. I'm multiplying in that 4. This is A, this is B. That's going to be equal to 4 times a half of, because that's what my identity looks like, sine of the sum minus sine of the difference, and then I simplify everything. So half of 4 is 2, sine of 100 degrees minus sine of 50 degrees. 150 are not special angles, so that's all I've got. I can't go any further. All right. We are down to the end. The last few identities, we did product to sum. Now we're going to look back the other way, sum to product. We're starting by adding and subtracting. We're going to end up with multiplying things together. I'm not going to show you how to derive these. You can absolutely find those online. If you want to walk through, want to play with it on your own, or you can use Khan Academy. I think my math lab has some videos that shows you how to derive all of these identities. Notice that my arguments are a plus b or a minus b over 2. These first 3 just start out as 2 sine or 2 cosine. You don't have to memorize. You do get to use your identity sheet, but you do have to pay attention. This last one, cosine A minus cosine B, is a negative 2 times the sine of the sum of half the sum times the sine of half the difference. Okay, so there's my 4 sum to product identities. We're going to make use of those in these final 2 examples. Here we have cosine of A plus cosine of B. That's this third angle right here, where A is 3 theta and B is 7 theta. We're going to use this one right here. Alright, so given this is my left side, cosine 3 theta plus cosine 7 theta, that's going to be equal to 2 times the cosine of, and I add, divided by 2, times the cosine of the difference in the correct order, divided by 2. So let's simplify. We've got 2 cosine 10 theta divided by 2 is 5 theta. Cosine negative 4 theta divided by 2 is negative 2 theta. Now, I don't ever leave an argument negative. But if I look at even-odd functions, I remind myself that cosine is an even function. So cosine of negative theta is equal to cosine theta. So this is an even function. Cosine is an even function. So I'm going to finish that off by saying, okay, that's the same thing as cosine 5 theta, cosine 2 theta. 2 times cosine 5 theta, cosine 2 theta. I'm just making use of my identities. Here we go again, sum to product. This is A, this is B. I'm doing sine A minus sine B. That's my second option up here. So sine A minus sine B is equal to 2 times the cosine of half the sum. So 2 theta plus 4 theta over 2 times the sine of half the difference. So 2 theta minus 4 theta over 2. Alright, 2 times the cosine of 2 and 4 is 6 theta divided by 2 is 3 theta. Sine of 2 minus 4 is negative 2 theta divided by 2 is a negative theta. And sine is an odd function. So sine of negative theta is the opposite of sine of theta. That means that negative comes out here. I can shift it all the way to the front. So I have negative 2 cosine 3 theta sine theta. And that is simplified.